Welcome back. In this unit we will explore rotational symmetry and the combination of mirror and rotational symmetry. In this picture you see a variety of cogwheels. And apparently this work team here is going to assemble them together to let them working smoothly like a clockwork. But I hope they will not assemble this gear wheel over here to the rest of this machine, because then it will not work anymore. Anyway, this is not our problem. These cog or gear wheels have different rotational symmetry of different order, ranging from 4 to 25. This picture should already reveal that objects can have any imaginable rotational symmetry. Let's have a look at some other objects. This three-bladed boomerang has a threefold axis of rotation, meaning that a rotation of 120 degrees around this axis in the center leaves the configuration unchanged. We mark this graphically with such a triangle, and the letter symbol is just the number 3. Flowers, or to be precise, the petals of a flower, often show rotational symmetry. One might think at first sight that this flower has a 6-fold axis of rotation, but it is, sure, only a 3-fold rotational symmetry, because there are 2 sets of petals, 3 smaller ones which lie underneath and in each case between these 3 larger ones. This car rim has, yes, 5-fold rotational symmetry. So rotation by 72 degrees will lead to a configuration that is indistinguishable from this one. As already hinted at before, there is no limit for the order of rotational symmetry. This becomes immediately clear if we look, for instance, at this glass of wine. Rotation along this axis at a completely arbitrary angle does not change anything. Be it 0.0001 degree or 31.74 degrees, this glass of wine has an infinite-fold axis of rotation. Some of these objects have only rotational symmetry, but others show also mirror symmetry. In general, there are far less objects which show rotational symmetry only without having mirror symmetry. It happens much more often that both symmetry kinds are combined. This car rim, for instance, has not only a 5-fold axis of rotation, there's additional mirror symmetry present. The question is, how many mirror planes do we have to specify for our correct classification? This is one mirror plane, but there are also these additional 4 planes as well. Well, to answer this question, you always have to look if any of these cutting planes, so to say, will generate different pieces, and if they are distinguishable or not from the pieces which will be generated from another of these planes. Here, all mirror planes are the same. They are identical, so we have only one unique mirror plane. And the full symbol is 5m. Let's switch to another example. This simple hexagon. This hexagon has, of course, a 6-fold axis of rotation. So, how many unique mirror planes are there? These lines in red are all the same. Why? Because they divide the hexagon in every case in the same fragments, as shown here. Or in other words, you can generate the other mirror lines by application of the 6-fold symmetry. If you rotate this mirror line by 60 degrees, you will generate this mirror line, and so on and so on. So this means unique are symmetry elements which are not generated by any other symmetry element. And this means here in the case of the hexagon, there is another set of mirror lines which cannot be generated out of this mirror line and rotation by 60, 120 and so forth degrees. Yes, these lines are mirror lines as well, and they build the second set of mirror lines, which are again, separately, interconvertible by this sixfold axis of rotation. And they generate fragments which are clearly different to these ones. But note, the red and yellow mirror lines are not symmetry related to each other. Because to generate a yellow line out of the red one, you have to rotate by 30 degrees, but rotating by 30 degrees is not a symmetry operation of the hexagon. Okay, the full description of the point symmetry of this hexagon is therefore 6 mm. I want to add one further aspect in this subunit relating to combining rotational and mirror symmetry. If you look again at this character h, with these two mirror planes, which are orthogonal to each other, perhaps you see that there is one additional symmetry element. Yes, of course, the twofold axis of rotation marked here with this green ellipse. The question is, why is this twofold axis usually not explicitly mentioned or noted? Why is it sufficient to denote only the two orthogonal mirrors, the horizontal and the vertical one? Well, because the two orthogonal mirrors implicitly contain the twofold axis of rotation. It is redundant to mention this axis. And this is a geometrical law. Any pairs of two orthogonal mirrors generate at their line of intersection a twofold axis of rotation. So the full but redundant symbol would be 2 mm, but usually only the short symbol is given mm. To finalize this unit, I want to come back to the core discipline of our course, crystals. There's one particular interesting aspect if we consider rotational symmetry in crystals. I said earlier that macroscopic objects may possess rotational symmetry of any order. In general, this is true, but not for crystals. Interestingly, and in contrast to other macroscopic objects, the order of rotational symmetry in crystals is limited to only these axes of rotation. We find 2, 3, 4, and 6, but not 5, and also not axes of order higher than 6 in crystals. We will explain this later in this course when we deal with quasicrystals. But for now, take this simply as an interesting fact. This is, by the way, the reason why all crystals of the world belong to only 1 out of 32 crystal classes or crystallographic point groups. The number of crystal classes is limited to 32, and this is because of the restrictions of the rotational symmetry in crystals.